Hi, and welcome to this quick look at how to use and apply y equals mx plus c in applied chemistry questions. It's a specific skill that comes up from time to time where you're dealing with a straight line graph and there's an equation of some description that is analogous or similar to y equals mx plus c, but it's sometimes quite tricky to spot that. So I thought I'd go through an example question where you might initially think what's going on, but then when you see it's very similar to y equals mx plus c, that opens the question up for you. So your basic idea is the old maths idea from pre-A level, that a straight line graph can be expressed using y equals mx plus c, and you can see that, that the c part is the y-intercept, the m is the gradient, which can be obtained by dy over dx. So this is our question. The first part of it is referring to the relationship between temperature and Kp, and they want you to complete the table by adding the missing values. I'll come on to that in a moment, but let's just first of all look at stating and explaining how increasing the temperature affects the position of this equilibrium, and whether the forward reaction is exothermic or endothermic. So as T increases, you can see that Kp goes down, and therefore that means that using the Kp expression, which is the partial pressure of products over the partial pressure of reactants, if Kp goes down, what's going to happen is the partial pressure of products goes down, whereas the partial pressure of the reactants goes up. So that means the position of equilibrium must be shifting to the left, the hotter the temperature gets. So that must mean in turn that the forward reaction is exothermic, so the endothermic direction is favoured, which is the reverse. So then it wants you to plot a graph of natural log of Kp against 1 over T using the axes provided on the previous page. Sorry, the next page. I'll show you that in a second. So this is our completed table from before, and this is the graph that I took from the mark scheme. It's easier just to use that as an example. You get a straight line at a fairly steep positive gradient like that. Now on the actual graph paper provided on the exam itself, they labelled the axes as such, with 1 over T as x and natural log of Kp as y. So if we look at the actual way that it's set up, equation 5.1, you can see straight away why we've put 1 over T on the x-axis, because those two line up. So that must mean the gradient is this value here, and the y-intercept, which would be down here off the screen somewhere, would be the natural log of Kp. So what we now need to do is get dy over dx to work out the gradient. Now depending on the actual line that you draw and the tangent you draw, the line that best fit through your points, the gradient can vary slightly from one candidate to the next, so they're quite flexible on the mark scheme as to what they allow. What they're looking for is you use your dy over dx. I happen to get 57,692. So obviously what you need to do is go to here. This is going to be your gradient. So you want to isolate delta H out of this whole expression here. So R is obviously going to be 8.314. That's the gas constant which you get on your data sheet. And multiplying the two gives you this value. Now the value for R is in joules per Kelvin per mole, so that would mean that it's in joules per mole, but you need to put it in kilojoules per mole and to 3 sig fig, so a little bit of final processing is required. So that gives us minus 480 as our final answer. Okay, I hope this has been a useful look at how you can apply y equals mx plus c. There are other examples such as the Arrhenius equation, which are slightly outside the remit of this question, but at least it shows you how a slightly applied question can actually be opened up using a fairly simple piece of maths. Okay, thanks for listening. Until next time, see you soon.